Hello students, welcome to AriserTalent. I am Arpita Sharma, your math teacher. So far we have studied Euclid's division lemma, Euclid's division algorithm, and in previous lecture we have done some questions of HCF and Euclid's division algorithm. Okay, so we will proceed our example with this one. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. So, remember what I have told you? In these kind of theorems and statements, you have to prove what you have to do first. You first have to write your Euclid's division lemma. And what's that? A equals to B Q plus R, where value of R is specified, right? Now, look at this and this expression carefully. 4q plus 1, 4q plus 3. Now, this 1 and 3 may be remainder. So, what's common here? 4q and 4q. So, what will be the value of B? Right, it will be 4. Okay. So, as the value of B is equals to 4q, this equation will become what? A equals to nothing but 4q plus R, where value of R is, now if value of R may be 0 or greater than 0 but less than 4, so what and what will be the value of R? Value of R may be either 0 or 1 or 2 or 3. Now stop here, because 4 cannot be the value here, or 5 or 6 or 7, that cannot be the value of R here. Okay, so what we have to do in our second step? Now put the value, of R equals to 0. So, at R equals to 0, this equation will become what? A equals to 4q plus 0 equals to 4q, right? Equation 1. Now, at R equals to 1, at R equals to 0, A equals to 4q, right? At R equals to 1, write the equation 4q plus 1, right? This is equation second. Moving forwards. Now, putting the value of R equals to 2, this equation will transform to A equals to 4q plus 2, right? Equation number third. Now, when R equals to 3, this equation will become 4q plus 3. Equation 4. Now, R equals to 4 or 5, we can't put it, it's beyond our limit. Now, we have to see each and every equation carefully. Now, in equation 1, A equals to 4q. It is an even number, obviously, because it's a multiple of 2. So, now 4q is what? Even number. And the reason is it's multiple of 2. right? Now, 4q plus 1. This is what? We have studied first that consecutive number of we have studied that consecutive number of an even number is odd number, and an even number and an even number plus an even number will be an even number. An even number plus an odd number will always be an odd number, right? So we will use this property here. 4q plus 1, 4q is even, 1 makes it consecutive number. In another way, 4q is even and 1 is odd. So it will give us an odd number. So it will be odd. Moving forwards, 4q plus 2. 4q plus 2. Now, even number plus even number. Even number plus even number equals to even number. So by this property, this is even, and now 4q plus 3. This is even number and this is odd number. Summation of even to odd gives you odd. So odd again. So now what we conclude? That this term 4q plus 1 and this term 4q plus 3 are odd. And look at here, what we actually have to prove is same. Show that any positive odd integer is a form of 4q plus 1 or 4q plus 3 where q is some integer. So we have proved it. So I will be giving you a question which is same like this question. So what you have to do is, you have to do it yourself, not the question. In this question, we will using the same properties and the method will be also the same. Okay, so do it yourself. Moving forwards, this is the question number 3 of your exercise 1.1. Mark it. The question is, an army contingent of 616 members. 616 members is to march behind an army band of 32 members. 32 members in a parade. The two groups are to march in the same number of columns. So, they have to march in same number of columns. What is the maximum number of columns in which they can march? Okay, so what it have asked to you? Some definite numbers of army contingents, AC, and behind the army band, AB, army band. Okay, so these rows will be of army band, that is AB, and these rows will be of AC. But number of these columns should be equal. Okay, if they are 1, 2, 3, 4, 5, 6, 7. So here also we will have 7 persons. Here we will have 7 persons. Here we will have 7 persons. Same for AC and same for AC. Same for AB and same for AC. Okay. Now, how we will do it? Look at the question and think. Any idea about it? Okay. So, when you look at very carefully, it is asking about nothing but HCF of 2 numbers. When you will find the HCF of 2 numbers, you can tell them that this particular number, in this particular number of columns, you may march them with equal number of persons in army contingent and army band. So, given solution is here. Given members in army contingent, so you have to write it in this form, in a language form in your board exams, right? Mark my words. These are given 616 now. Behind the army band of 32 members. So, members in army band. That will be obviously less. Army band. That's given what? 32, right? So, applying Euclid's division algorithm. Why algorithm and not lemma? We will using the equation of lemma, but we will follow step by step procedure. So we use the word division algorithm here. Okay. This is for rough work. 616 dividend, we have done this before, and the 32 is here. Now, one time 32, 9, 2, 6. Now 32, I guess 9 times 18, 28, that's 288. We'll do this calculation here and we'll write it in language form afterwards. 616, this will be our dividend, and 32 divisor. Okay, now the process starts. One time 32, remainder 9, then here 2, okay, 6. Now 32 to 96, I guess 9 times. So let me calculate. 288. Yes. 2, 8, 8, 8, 0, and again 0, right? So, here our divisor will become dividend, right? 32, 4 times, and the remainder is 0. Remainder is 0 here. So, what will be the HCF of these two numbers? 8, right? So, putting this into a language, applying Euclid's division lemma, 616 is equals to 32 multiply. Okay, so we'll put it in language. 616. This is our dividend and the divisor is 32 multiplied by what? Question 19. Okay. And the remainder is here. 8. Don't confuse it with 296 or any other. Okay. The remainder, last remainder is 8. Plus R. Then the remainder is 0. No, it's not 0. So, step 2. Because your remainder is not 0, so you will apply. Now, 32 is now your dividend and 8, the remainder is your quotient. Multiply by what? 4. And the remainder is 0. So, hence remainder is 0 here. So, this number, which is your what? Divisor, is HCF of 6, 1, 6 and 32. Okay. And it's also HCF of 32 and 8 also. Okay. So it is 8. So what? Our answer is what? So 8 is the maximum number of columns in which they can march. So now you can see how will they march. They were having 32 members. So first member, second member, third member, fourth member, fifth member, sixth member, seventh member and eighth member. These are 8th member of, these 8 are members of band, army band, hai na? Okay. And behind them all other first band members and then contingent members will stand, right? This will be the answer. Okay. Note it. Okay. We have done the question and we have done some statements to be proved. Now, the next is prime factors. What are prime factors? So, we have talked about prime numbers. What are prime numbers? Any number which is divisible by only either 1 or itself. Let me say A is any prime number. So, if A is any prime number, it may either be divisible by 1 or may be divisible by A, nothing else. Now, by default, 1 is not a prime number. Mark this. 1 is not a prime number. Okay. So, we will start from 2, right? Then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and rest you will do. So, 1 is not prime number. I have told you. Now, 2. What can be the possible factors? What can be the possible factors of 2? And any other numbers? Any other factorization possible of number 2? No. So, first is 1 and second is itself. So, it's a prime number? Yes. Now, factorization of 3. 1 multiplied by 3. Now, any other possible factorization? No. So, it's a prime number. 4. 1 into 2 into 2. Okay. So, 1 is the factor and other than itself, 4. It is having another factor that is 2. So, it's not a prime number. Not a prime number. Then 5. 1 into 5. Any other possible factorization? No. So, it's prime. Then 6. 1 into 2 into 3. We'll factorize in smallest numbers possible. Okay. So, it is not a prime number. Now, 7. Divisible by 2? No. Divisible by 3? No. 5? No. Okay. 1 into 7. That means it is prime number. 8. 2 into 2 into 2 into 2 into 1 also. Okay. So, not a prime number. So, it is prime. It is prime. It's not a prime. It is prime. 5 is prime. 6 is not a prime. 7 is prime. No, no, no. 11. Yes. 13. Yes. So, you can go on to infinity and find infinity numbers which are prime. Okay. So now, why are we studying this? We do any work if there is benefit of that particular work. So, right, these prime factors are of our use. Okay. Fundamental theorem of arithmetic. So, in this particular theorem, we will use the concept of prime factors. So, we was studying that, right? Every composite number can be expressed as a product of primes, and its factorization is unique apart from the order in which the prime factor occur. Now, these are important words. Okay. Now, what is the meaning of every composite number can be expressed as a product of prime? You have any number from your integers. Okay. So, if you will like 2 or 3 or 4 or 5 or 6 or any number, it will be a factor. It will be made from the factors of prime numbers. Like we have studied 2 is prime, 3 is prime. Now 4. 4 is a composite number. Composite is which is composed of 2 numbers. And 2 numbers is what? 2 numbers are what? 2 or more numbers are what in this case? These 2 or more numbers are prime, only prime numbers. Okay, so smallest division of these numbers are only prime numbers. Likewise 2 and 2, these 2 are prime. In this case 2 and 3 are primes. Okay, now factorization unique, its factorization is unique. Now this factorization 2 multiplied by 2 is unique. Now see, this factorization is 2 by 3 and this is 2 by 2. 2 multiplied by 2 and 2 multiplied by 3. Apart from the order in which the prime factor occur. Now it's saying that factorization is unique. It doesn't mean that you will say it is 2 by 3. I can also write it like 3 by 2. Order can be reversed. It's saying apart from the order which it occurs. So it can be 2 by 3 or it can be 3 by 2. Okay, but there is always a unique factorization, prime factorization of every composite number, right? So this is our theorem of fundamental. This is a theorem of arithmetic, right? And we are going to use it in further section. LCM and HCF. We have studied HCF earlier. Now we will study LCM, least common factor, and you have studied all these two things in your earlier classes, but we will study it now also. Now let me explain it with an example. 26 and 91. We will be taking HCM and LCF of both two numbers. Now HCF and LCM. The numbers are 26 and 91. The very first thing we have to do is do the prime factorization of these things. Okay. Now, prime factorization of 26. 2 multiply by 1, 3. Now 2 is prime and 13 is also a prime number. So factorization stops here. Now 91. Okay. So it is divisible by not 2, not 3, 5 not 5. Then 7. Okay, it is divisible by 7. 7, 1 time, 3 time. Okay, 7 multiplied by 13. You are seeing this? Prime factorization of 26 is 2 multiplied by 13 and prime factorization of 91 is 7 multiplied by 13. Now, if we are talking about HCF, we have to exclude our commons here. So, 13 is common in both. Okay. So, we will write 13 as HCF of 26 and 91. Right? HCF 26 and 91. Now, LCM. The factorization are again 2 and 13 and 7 and 13. Prime factorization are same. Now, we have 13 common. So, first we will write the commons here. 13 is common. Okay. Now, what is left? 2 is left. 7 is left. Okay. So, it will become 13 into 14. Now, 13 multiplied by 14 is 12. 5 and 13, that will become 182. Okay. So, LCM of 2, 6, 26 and 91 is 182. You are seeing the difference here? In HCF, we are only taking the common factor. Okay. In LCM, what we are taking? We are taking first the common factors and then the left ones. First, taking out the common factor and then the left ones. And we will multiply them and you get the answer. This is the difference between HCF and LCM. It's clear to you all? Now, what is for you? You will find the LCM of 510, 92 and also its HCF. Right? Okay. This is for today. In next class, we will discuss some more questions on this theorem. Thank you.